Hello everyone, my name is Adam Awade and my teammates are Muhammad Arkebat and Michael Baris. We're from the University of Illinois at Chicago and we're presenting the final project for ME312 Dynamic System and Control. In this project, we're developing a controller which will minimize the desired angle of the skeleton. The controller will have a closed-loop feedback mechanism to provide the command signal that will minimize the error. The angle will be maintained by holding the rotor position. The input to the rotor is an armature voltage signal in volts. The motor provides an output torque, which drives the system. Magnetic flux is provided by a separate field circuit, which is assumed to have a constant field current. The armature current is controlled through the armature voltage. Effects such as hysteresis and the voltage drop across the brushes. The magnetic flux produced by the field circuit is linearly proportional to the field current. Here, as shown in Figure 1, the circuit diagram of DC motor. The input to the motor is an armature voltage signal. In volts, the motor provides an output torque, which drives the system. Magnetic flux is provided by a separate field circuit, which is assumed to have a constant field current. This block diagram has a plant and a controller. In our case, the controller can be PI or PID, as required for their plant. Controllers. Proportional integrated derivative, or as known as PID, is an instrument which is used in industrial control applications to regulate temperature, flow, pressure, speed, and other process variables. The PID controllers employs a control loop feedback mechanism to control. The PID controllers is named after its three correcting terms. They are proportional, integrated, and derivative, and these are summed to calculate the output of PID controller. To understand the function of PID controller, consider the following block. This is a diagram. Will show how the controlled input is given to the industrial via PID controller. Figure 4 shows the actual diagram of PID controller, which has three types of control, as proportional control, derivative control, and integral control.
Here we have a second order control system with PID controller diagram. As you can see, we have the proportional control, the integral control, and the derivative control. And we also have the system block at the end. And then it goes and it reads that and goes to the unit feedback and starts over. Here we will find the equations for the transfer function of the PID controller with the second order system. We're given this original equation, and we know that G of S equals this, H of S equals 1, and by plugging those in, we get this equation, and to simplify, we get this final answer here. We use a PID controller in different applications for different purposes. For example, when we need to keep something constant like temperature, then we use a system in a closed loop feedback to give the desired output. To obtain desired output, we simply need to put the setting in the controller and keep it, and it will keep the output constant based on the feedback from the input. The second example is to use a PID controller in our vehicle for control of speed. They were used as cruise controls in vehicles. First, we get the speed we're going, then we set our cruise control. Then the cruise control sends output signal to the speed regulation system to regulate the speed. The speed sensor provides feedback signal to tell the cruise if the car should speed up or slow down.